Welcome to our structure-sponsored webinar, Corrosion Mitigation of Traditionally Reinforced Concrete Structures by MAPEI. Thank you for joining us. At any time, you may adjust your audio using any computer volume settings you may have. This session will be recorded and made available later on the Structure Magazine website. On the bottom of your screen, you will see the Q&A pod. To send a question, click in the text box and type your text. When finished, click the send button or push enter. All questions that you submit will be addressed at the end of the presentation. We are joined today by our speaker, Brian Stratman, PE. Brian is the Business Development Leader for Corrosion and Structural Strengthening with the MAPEI Corporation. He has over a decade of experience related to the design and installation of FRP strengthening systems for concrete and masonry structures and is an NACE certified cathodic protection technician. Brian is also an active member of the ACI 440 Strengthening Committee and the ICRI Strengthening and Corrosion Committee. At this time, I will turn the floor over to Brian to begin the presentation.
Today we're going to be talking about corrosion mitigation of concrete structures, traditionally reinforced concrete structures. So not your post-tension, not your pre-stress, just regular traditional rebar reinforcing. The post-tension, it's a little bit of a different animal, different requirements and such. So we're gonna stay away from that today. But we're going to basically be talking about, with the basics, so just real basics of corrosion. Not a real deep dive into the chemistry of it, because it would take too much time, and really it's pretty complicated anyhow. But just you have to have a basic understanding of the corrosion process in order to allow you to better assess, what may be causing your corrosion, and what effects to look for the different types of corrosion that may be happening. And then, finally, to just select the appropriate mitigation technology for your various repair projects, so that you don't wind up with a bridge that looks like the bridge we're looking at here, which, believe it or not, was actually repaired and put back in service without being knocked completely over. So you can let things get pretty far gone and still bring them back to life. Obviously, there'd be quite an expense with doing so, but hopefully we won't let anything get this far bad before we decide to do something about it. So there's really a few different causes of corrosion in concrete, and really it's always due to a change in the chemical environment in the concrete. This change in the chemical environment can be caused by several different things. The most common, of course, is going to be chlorides. Whether you're in the north like me, getting ready to enter our winter months where we're dumping road salt all over our roads and highways. Or maybe you're on the coast and you've got airborne chlorides blowing in off the ocean. There's quite a lot of chlorides that either are naturally, being absorbed by the concrete, or there's plenty of chlorides that we're also just unnaturally putting there for various purposes, such as de-icing the roads. There's also the process of carbonation. Carbonation in and of itself isn't actually directly cause corrosion, but it does create the environment that will allow corrosion to start and really take off. So we'll talk about that a little bit, a couple slides here. And then lastly, some sort of chemical attack. This could be sulfates, any type of, industrial environment where maybe we're putting some chemicals into the air, or they're getting into the concrete at the plant. Not as common certainly as chloride induced corrosion, but still happens from time to time, something to be aware of, particularly if you work in that industrial environment. So with any new concrete, when you freshly place concrete, corrosion usually doesn't exhibit itself for at least probably 5 years, 10 years, maybe 20, 30 years. And the reason that new concrete doesn't typically start corroding right away is because when we pour fresh concrete, something happens at the reinforcing steel where we get the formation of what we refer to as the passivation layer. You can kind of think of it as almost like a rubber sheathing around the rebar, where it's like a protective layer that forms around the rebar, and it basically allows the steel to repel the chlorides. So it's more or less like a natural defense system. And what happens over time as the pH of the concrete starts to lower, fresh concrete's going to have a pH typically 12 or higher. But as time goes on, as carbonation is allowed to take place, that pH is going to start to drop. And as the pH starts to drop, then the passivation layer can be breached. Once the passivation layer gets breached, now we have a situation where corrosion can start to actually happen. So there's two different ways where this passivation layer can be breached. The first has to do with chloride ion concentration. I put a number of 330 parts per million due to either chloride, or this could be also chemical attack. If it was sulfates, there's probably a different number for sulfates, but chemical attack can also breach the passivation layer due to a certain concentration of the chemical. So as more and more chlorides get into the concrete and start to reach the steel and penetrate, either again through road salts or airborne chlorides on the coast, that passivation layer is going to be broken down over time, and then corrosion is going to be able to start. The other way that it can also be broken is through a loss of alkalinity that I mentioned before. So as the pH of the host concrete gets to about 10 and starts to drop 9.5, 9, then you get a process called carbonation that starts to take place. Carbonation will also breach the passivation layer. So while I mentioned that carbonation in and of itself doesn't actually cause corrosion of the reinforcing steel in a way that we're really concerned about, it does create the scenario where we have perfect conditions for that type of corrosion to happen. So it's something to certainly be cognizant of and be aware of. So yeah, as the steel starts to corrode, what happens is that passivation layer gets broken. Now the chlorides are able to reach the iron. Most of our rebar is iron oxide. So it gets through the passivation layer, starts to react with the iron in the rebar, and now we have the creation of a corrosion cell, which starts the corrosion current and all the bad things that we see with corrosion. So that's basically what happens. We've got chlorides now in contact with the iron, and the whole show starts from there. With carbonation, carbonation happens almost immediately once you start placing fresh concrete. So you'll see that top equation there: calcium hydroxide plus carbon monoxide, or excuse me, carbon dioxide, reacts to create calcium carbonate and H2O. So that's that top equation there. If any of you are chemistry buffs, I apologize if I mispronounced anything there. It's certainly never been my forte on the chemical side of things. However, the calcium hydroxide does react with the carbon dioxide, and you get that calcium carbonate in the presence of water. So you have to have wet concrete. If you're in a really dry, arid environment, Las Vegas, Arizona, somewhere like that, this process doesn't actually happen because it's just so dry. But it does begin pretty much immediately after the placement of concrete when the conditions are right. Those conditions do include a relative humidity between about 40% and 90%, which is pretty typical for most areas where outside of, like I said, Las Vegas, Arizona, some of the drier, more arid environments. So the effects of carbonation, basically, what happens is it reduces the porosity of the concrete. So you start to get those calcium carbonates forming within the concrete. So that's actually a good thing. So what that means is we with the formation of the calcium carbonate, we're getting a more dense concrete. Well, a more dense concrete, as some of you might be aware, is actually going to have a higher compressive strength because it's got more ability for load transfer between the aggregates and the carbonates that have been formed. So you actually would see a slight increase in your F prime C, your concrete compressive strength, due to carbonation. So that's all well and good. However, as I mentioned, it also reduces the alkalinity of the concrete. So by reducing the alkalinity of the concrete, it helps accelerate the time until the passivation layer on the reinforcing steel is able to be penetrated, and shortens the natural protection life of that reinforcing steel. So in a nutshell, carbonation, once carbon is fully carbonated, it's going to reach a pH of about 8.5, which clearly is well below that threshold that I gave you of about 10, 9.5, 10. So it's going to create those conditions again where corrosion can start to initiate. The chlorides are going to really start to attack the reinforcing steel, and we'll start to see the rusting and the spalling, cracking of concrete that we all know to be typical of corroding concrete. So with that, that's just, I wanted you to know just a little bit about carbonation. It's something to be aware of. There's, like I said, there's nothing you can really do about it. You can't place concrete that has no exposure to carbon dioxide. It's pretty tough to do. So it's just something to be aware of, certainly on the planning side of things. But from here on out, really, we'll be talking about chloride-induced corrosion and its effects, causes, and things that we can do to kind of slow that down. So what are some of the sources of chlorides? Like I said before, that could be certainly when I'm in Ohio, we're getting ready to get into our winter months. Once it starts snowing, we start throwing salt around like it's just sand all over the place. I mean, you got salt in your shoes, salt in your hair, salt in your clothes. But salt is really good at melting ice. So for the winter months, it's very effective at keeping our roads clear and safe so that we can all get to work and school and wherever we need to go safely. You also have chemical plants that could be inducing some chlorides into the air. Certainly water treatment plants use a lot of chlorides as part of the process. So there's different places that chlorides could come from. Those are the more external sources, but then there's also these internal sources that we need to think about as well. So mixed water, what's one thing that people don't often think about, but we do, as I mentioned, use chlorides to treat our drinking water. So there's going to be limitations from the EPA on how much chloride can be put into that mixed water. So it's not a huge amount. Typically, some parts of the country don't use it at all. But there could be some small amount of chloride in the water that you use just to mix the concrete. There's really no way around that. You know, when you go to get your water, you got to go to the faucet. You're going to get whatever comes out of that faucet. Aggregate is another one that people don't often really think about, but if you've ever seen an aggregate plant, we have quite a few here actually in Cleveland where I live. They just pile just massive mountains of rocks. They're typically separated by sieve size so that they, when you get a mixed design, you can order up, however many pounds of that size or this size. But as those piles are sitting there, they're below, in the case of, where I live here in Cleveland again, they're right below a traffic bridge. So as the snowplows are going by and dumping road salt, and then the cars are driving and they're crushing up the salt, and you're getting all sorts of chlorides into the air, they're going to then settle down onto that pile of aggregate down below. So one thing you'll see a lot of times in specifications that they want you to use clean, washed, dried aggregate. The reason they say that is they want you to wash any chlorides that may have accumulated onto that aggregate as it's, as it's sitting in the plant, waiting to be used. So it's real important to pay attention to that, particularly if you're getting your aggregates in a place where we do use road salts pretty commonly. Then the third one there, admixtures. ACI, now the 318 guidelines are pretty stringent on use of use of chloride as an admixture. It's very, very, very small amounts are allowed, pretty much almost zero. However, I work on the repair side of concrete, so we see a lot of buildings that were constructed in the the 60s and the 70s, prior to ACI really realizing that these chlorides were a problem. So back then, they actually used chlorides as an accelerant in the winter months. They would add chloride to the concrete, which would allow it to basically set faster. So it would speed up the construction process in the winter months. What they didn't know, of course, at the time was that by adding all those chlorides to the concrete, they were creating a really tough situation down the road once all the corrosion started to initiate, which of course it did. So oftentimes when you go to a big city like Chicago, New York, you can kind of tell the buildings that were built pre 1970s, 1975 or so, because every 4 or 5 floors of the structure look really good. Then you got 4 or 5 floors of the structure that you can tell they've done a lot of repair work, a lot of cracking, spalling. Those are typically the floors that were built in the winter months when they were adding the chlorides to the concrete unwittingly. So since then, it shouldn't be an issue nowadays. They're, again, really stringent on how much can be added. But there, of course, are older buildings where it's still an issue. Then we have our external sources. So, like I said, we use chlorides as an admixture. So we use chloride as an admixture. So those are going to be, again, the de-icing salts. It could be, precipitation from the rain. If you get airborne chlorides, that's going to help bring down some of the chlorides, certainly along the coast when it rains. And I put contractors there almost, half jokingly, because I've seen contractors do some pretty crazy things over the years. And one of the things that they can do is, if they're doing certainly like an oceanfront project, they're a little short on water, they got a little bucket, they see their bucket, they see the ocean, they're like, yeah, you know what, I'll just go and get a bucket of water out of the ocean. Well, of course, the ocean is salt water. Bad idea. Don't want to be adding that ocean water to your concrete mix. So not something that's going to happen all the time, of course, but I mean, it does happen. So it's just something to be aware of, and make sure, of course, that it's not being done. This slide, I pulled this slide. It's from several years ago now, obviously over 20, 1998. This study was done, but I really like this slide because it shows you what you're looking at is a map of airborne chlorides in the United States. So, oftentimes when we're in coastal areas, we think, okay, it's really only a problem for those oceanfront balconies. Of course, most of us are probably familiar with what happened in Florida a couple of months ago with that building collapse. We certainly are most concerned with buildings that are right on the coast because they're getting, blasted with the most chlorides at a pretty constant rate. But when you look at this map, you can certainly see that they're getting very, very high concentrations of airborne chlorides several hundred miles inland from the coast. So it's not just an issue right along the coast. Really, anywhere that's within, I would say, probably 200 miles of the coast is at risk of being exposed to airborne chlorides. So it's not just the really wealthy oceanfront homeowners that have issues with this. It certainly extends way back into those coastal areas. Certainly you don't see it as much out in California, where again, it's a lot drier. Humidity is a big factor in corrosion and how much corrosion takes place. So in California, where it's a much more dry environment, you don't see as much corrosion along the coast as you do, say, certainly in South Florida, where it's just super humid all the time, or anywhere in the the southeast parts of the country, where that humidity really comes into play. But the results, as we all know, are never good. Once corrosion starts, it's always a problem. The reason for that, of course, is as iron is converted to iron oxide, which is another word, fancier word for rust, it starts to occupy a lot more volume than the original reinforcing steel. So studies have shown that once a piece of iron starts to starts to rust, it actually occupies about 4 to 10 times the volume of the original steel. So that's obviously a problem in concrete, where we have very poor tensile capacity in the concrete. As you start to have that expansion of the rust or expansion of the steel inside the concrete, it's going to induce a lot of tensile forces on that concrete. It's going to lead to the cracking and the spalling that we see that's so typical of corrosion damage to concrete. So that's where the cracking and the spalling comes from. And then, of course, there's the other side of the coin, where we have actual loss in volume of the steel as it rusts and flakes away. We see that picture on the left there. That piece of rebar has lost quite a bit of its area due to corrosion. So as we lose steel area, we of course lose capacity. And as we lose capacity, then we're at danger of structural collapse, which is of course what we're all trying to avoid. So it really becomes a kind of dual issue. You've got the issue of the cracking and the spalling, which kind of exacerbates the corrosion issue, because more water, more chlorides are going to get in as it's cracked and spalled. But then you have the other problem too, where you're losing the capacity of the steel. So it's really something we can't ignore. We do need to do whatever we can to address it and make sure that we're avoiding as best we can corrosion of the reinforcement steel. So I won't spend a lot of time here. This is the chemistry side of corrosion. So really what I wanted to point out here, and there's a couple important things to really take note of. And I put at the bottom, put more simply, rebar plus chlorides plus water is rust or corrosion. So that's the simple way of looking at it. Up top is the more involved way, but really the takeaways from those equations up top are that all of the or anything that's a reactant, so anything on the left side of those equations, you will also find on the product side of things. So, chloride isn't consumed in the chloride. The reaction of iron with chloride doesn't consume the chlorides. It just binds them to the iron to create that iron chloride ion on the right-hand side there. So the reason I wanted to point that out is that it's not something where, okay, well, we accidentally got some concentration of chlorides into the concrete. It's going to start corroding, but in 5 years, all those chlorides will have eaten themselves up. They'll all have reacted, and it won't be an issue anymore. That's not how it works. Those chlorides are going to remain free in the concrete to react. So it's a cyclical thing. So once once corrosion starts, it's really never going to stop unless we intervene somehow to put it to a stop. So that's really the important takeaway from that equation, more than certainly trying to memorize any of those. You certainly don't need to know those equations on a day-to-day basis. But when you do get a corrosion cell, you're always going to have an anode site and a cathode site. So at the anode site, that's where the corrosion is actually happening. So we can see in the picture here, we've actually had a rupture of the reinforcing bar, completely broken half. But just a few inches down that bar at the cathode site, we've got completely clean steel that looks like it's in great shape. So that's pretty typical of a corrosion cell in concrete. You get this really, concentrated corrosion action happening at the anode, and then just a few inches away at the cathode, everything looks fine and dandy. So it's certainly an issue because you get pitting corrosion when that happens. Really, pitting corrosion is really severe, aggressive corrosion at one small pointed area of the steel, which is going to result in rupture of the steel like we see here. So that's obviously something we don't want to have happen. So, what drives corrosion? Really, it's the electromotive force. So corrosion is measured when you're talking corrosion currents. What you're talking about is the flow of electrons between the anode and the non-corroding cathode. So one way to think about that is it being a waterfall. So that flow of electrons is creating a potential difference between the anode and the cathode, a difference in electrical potential. That difference in electrical potential is known as EMF or voltage. So if we think of the corrosion cells being a waterfall, a really small, short waterfall isn't going to generate a whole lot of energy. However, if we have a really big waterfall, like I believe this is the American side of the Niagara Falls here on the right, that's going to create a lot more energy. So when we think of that in terms of a corrosion cell, the bigger the waterfall, the more severe the corrosion is going to be, because that potential difference, that energy that's being created between the difference of voltage at the cathode and the anode becomes very large. That's when the corrosion current starts to become very, very high. So again, very similar to a waterfall, just the taller the waterfall, the more energy that's created when it comes to a corrosion cell in concrete, the greater that potential difference, the greater the corrosion current is going to end up being. And then that would, of course, dictate how soon we need to address that corrosion in the field. So with that, that's kind of all of the chemistry and background stuff. So now we'll get into actual products, techniques that can be used to actually address corrosion in the field, and how can we stop this beast from ruining all of our structures. So really, there's different ways of doing it, but they all come back to this breaking the chain idea. So in the corrosion cell, we're always going to have four really different things happening. We're going to have the formation of that anode and cathode. In concrete, concrete serves as the electrolyte, the kind of the moisture-rich environment of the concrete. It serves as the electrolyte, which allows this whole process to happen and carry that current from one place to another. Then, of course, we have the fuel, which in our case is the chloride. So that's what's going to be feeding this whole the whole cycle is going to be those chlorides coming in, and then there's the pH of the system. So if we're able to manipulate any one of those four things, then we can slow down or prevent corrosion. So what I like to think of it as breaking that chain, breaking that corrosion chain. So if we can prevent the reinforcing steel from functioning as an anode at a given location, for example, by using galvanic anodes or rebar coatings, which we'll talk about, we can actually prevent the corrosion from actually happening. So getting rid of the anode and cathode is one way to address corrosion in the field. Another way is to eliminate the electrolyte. If we eliminate the pathway for the ions to travel between the cathode and the anode, again, the corrosion cell is going to stop. So elimination of the electrolyte would be a great way to break the chain. Then, of course, we could simply remove the chlorides. Well, that's a lot easier said than done. There actually are ways to chemically remove chlorides from concrete. However, it's very, very expensive, and it's very, very time consuming, and it involves closing entire parts of your structure for lengthy periods of time. So it's really most of the time not practical to do that. So what we can do though is we can raise the concentration limits. Remember I said 330 parts per million, give or take, was the concentration of chlorides that would break the passivation layer. Well, what if we're able to raise that concentration to say 700 parts per million or 800 parts per million? Now we're preserving that passivation layer for longer, and we're delaying the onset of corrosion. So that's one of the ways that we attack the problem. And then the last way is, again, with that pH, if we can raise the pH back above the threshold, if we can get it back up to 12.5, 13, that's another way that we can break the chain and stop this cycle from happening. So all of the products, all the technologies that we're going to run through here in the next 15 minutes or so are going to, in somehow, way, shape, or form, fit into one of these four categories of breaking this corrosion chain. So the first way we do that is just simple concrete admixture. So again, I work in the repair side of things. So pretty much all repair mortars anymore are going to say, with integral corrosion inhibitor. And then I don't work with a whole lot of fresh concrete, but I'm sure they're adding these to fresh concrete as well. Really, all that it is nitrites. It's calcium nitrite. It gets added to the bagged concrete or added at the mixed plant in the case of new fresh large batch new concrete. And all the calcium nitrate does is it raises that concentration level from 330 up to some higher number. Supplemental cementitious materials, SCMs, also do this as well, more so by just increasing the density of the concrete. By increasing the density of the concrete, you get less chlorides that are able to penetrate through the pore structures of the concrete. So it just slows it down from that avenue. But again, all these are delaying the onset of corrosion. These are not going to prevent corrosion. At some point, you're probably going to still exceed that corrosion threshold. It's just going to take longer to do so. So if you're on the front end designing new concrete or using a fresh bag of repair mortar concrete, this is just a good, cheap way to just slow things down and buy yourself a little bit of extra time until the corrosion starts to happen, and frankly, becomes more of an issue at that point. So not really a product that's going to prevent corrosion. It's just going to slightly delay it, but it's very cheap and easy to do. So frankly, I would like to see it done on every batch of concrete that we do. It'd be great. Because it's easy to do. It has minimal effects on the performance of the concrete, and it just buys you that little bit of extra time. Then there's alternative rebar. So this is going to prevent electrochemical reactions from happening altogether. These are going to be your carbon fiber rebar, glass fiber rebars. They're starting to explore a little bit with basalt fiber rebars, but all sorts of different composite materials. But this would also include epoxy coated steel rebar and stainless steel rebar, which are more robust forms of steel reinforcing. Of course, more expensive, but really all of these, what these are all doing is they're basically creating a reinforcement mechanism that isn't going to corrode at all. That's true certainly of the carbon and the fiberglass. Stainless steel will corrode eventually. It just takes a lot longer for it to happen. And then epoxy coated steel, of course, is going to corrode once the epoxy is breaks off or if it has any pinholes or things like that. So it's a little less effective than certainly carbon or fiberglass. But the issue with some of these, of course, carbon and fiberglass, the building code does not allow us yet to completely build a structure out of carbon and fiberglass bars. There are some privately owned structures out there that are being used in that capacity, but they're privately owned, so they can get away from using some of the building code requirements. But if you have to follow 318, the 318 building code does not allow you as of yet to use FRP bar as the main reinforcement system for your structure, mostly due to fire concerns, but I won't get into that, and that'll get us out into the weeds quite a bit. But these are very very useful. I'm not a big fan of the epoxy coated bar. If you get any kind of pinhole damage, then you're going to get a lot of corrosion right at that local area. But it's certainly, it's better than nothing. If you're going to do nothing or epoxy coated bar, then certainly epoxy coated bar is a good way of more slowing things down. Again, it's more similar to those the supplemental cementitious materials admixtures. It's not really going to prevent it long term, but it's just going to slow it down. Whereas the carbon fiberglass would really completely prevent corrosion altogether from happening, which would be great. We do sell some carbon bars, MAPEI rod system, but we are not selling large quantities of it. We are more, again, on the repair side of things. So we do some localized repairs. Generally, when you're on the top side of like a slab and you need to do some localized negative moment reinforcement, you can use carbon bars as that reinforcement and like a little saw cut, and then know that it's never going to corrode. So it's a great little product for some kind of small limited applications. But we're of course not a rebar manufacturer, so we're not going to be selling truckloads and truckloads of this. We're more selling 10 to 50 feet or so of bar for a small use project. Then there's waterproofing. So waterproofing, really, again, this is another preventative measure. It's not going to ultimately stop corrosion, and it certainly doesn't reduce active corrosion, but what it does, slow it down somewhat. So the idea of waterproofing is we're keeping the water out. Remember back to those series of equations that I showed, you had to have water as one of the components. If you don't have water, well, the corrosion cell can't function, it can't operate. So if we keep it dry, we don't have to worry about corrosion. That's of course a lot easier said than done for a lot of different reasons, but certainly, if you're going to have exterior concrete and you're going to be in a chloride environment, putting some type of waterproofing system down it should just be done all the time. It's going to delay the onset of corrosion. It's going to prevent a lot of the cracking and the spalling that happens because of it. It's going to protect the capacity that you need in that concrete. So really good, smart thing to do, really, if on exterior concrete. Some of the systems that we are those Planet-Seal WR40. Those are more like subgrade waterproofing. In parking garages, we have our MAPEI system. Those are the urethane coatings. If you go into a parking garage, you'll see a lot of times looks like a gray paint that's on the concrete. That's actually a waterproofing system. It's a urethane that they put down to provide some better adhesion for the cars, but also to keep water from getting into the concrete and causing corrosion issues. So should be done. Again, it's usually pretty cheap, easy thing to do. Not going to actually reduce active corrosion, but it will slow down and prevent to some degree the initiation of corrosion over time. Remove and replace. So you're out on a bridge deck and you see a bunch of concrete's cracked and spalled. You do some investigation. You quickly determine that it's got corroding reinforcing steel. So the idea is you just cut it out of there. It's bad shape. It's got some chlorides. Let's just cut it out, remove it. There are certainly hundreds of repair mortars that are out there on the market. We talked about some of them having integral corrosion inhibitors as well. Sounds all well and good. It's going to stop corrosion in that repair area because we've removed the chlorides from that area. So no chlorides, no corrosion. But we've got to consider what we call the incipient anode effect. So, in a corrosion cell, what we talked about having that anode and cathode. So we've got the anode where the corrosion is happening, and we've got the electron flow out of the anode over to the cathode. So this is, and then of course the electrolyte is the surrounding concrete. So the excess electrons are consumed in a series of reactions. The cell starts formulating, you get this continuous cell of rusting of the reinforcement bar. Well, what happens when we all of a sudden repair an area and we cut out the area where high pH, it's gonna create a passivation layer on the reinforcement steel. Everything's gonna be great in that repair area. We're not gonna get any corrosion. Well, what do you think is going to happen right next door to that? If you think back to that waterfall example again of electromotive force and difference in electrical potential, now we have this really clean, chloride-free, high pH patch area that's right next to a low pH, probably chloride-saturated area of concrete. We've got a huge difference in potential at that area. So what would you expect to happen? Well, you're going to get corrosion right next to the patch area, which is almost always going to happen. So we call this like chasing the repair. So if you just cut out the concrete, patch it up, you don't do any anodes or rebar coatings or anything like that to address it, I can promise you that in 5 years, the owner's going to call you and say, hey, you remember that patch that you just did? Right now, right next to that patch, it looks just as bad as the original patch did. I need you to come out and take a look at it. Well, if you do it again and then you don't use anodes or rebar coatings or something to address the anode, the halo effect, it'll happen again and again and again. So it's not uncommon to see concrete surfaces where you have just all these repairs, one after another after another. And again, that's just an ignorant or less informed engineer that doesn't really understand what's happening. So it's really important to take note of this when you're doing repair areas so that you don't do this, what we call it, chasing the repair, because you will just find yourself every couple of years going back and having to do another repair and another repair, another repair. So what do we do about that? There are things you can do about that. One of the best things you can do is to use galvanic anodes. Sacrificial galvanic anodes are generally zinc. They're made out of, they have like a zinc, a lot of them call them hockey pucks because they're kind of round shaped like a hockey puck. Some of them are more rectangular. There's different kinds, shapes, types. But what all of them are doing are basically artificially shifting the electrical potential of the reinforced concrete by connecting a preferential element to that rebar. So there's something called electromotive series where all of the different metals are ranked. And as you move down the electromotive series, a metal lower on the list is going to be more likely to corrode than a metal higher on the list. So by connecting that zinc right to the iron and the steel, zinc is more noble, they're less noble than the steel. So it's going to preferentially corrode in the presence of steel or zinc. So what we're doing is, instead of allowing the corrosion to happen in the part of the concrete that was immediately adjacent to the repair, we're going to force the corrosion to happen within that little puck, so that we don't damage any of the concrete around us. Again, typically use zinc. I'm not sure of any other systems out there that are using anything other than zinc at this point for the anodes. But they're very, very effective. It's going to be time limited depending on how much zinc you use. So typically 100 grams or so is kind of the average amount. But you can get anodes that are up to 300-400 grams of zinc. You can get them as small as some manufacturers are selling, like 38 grams. But the more zinc you use, the longer it's going to take for it all to consume itself. So the longer that anode is going to prevent corrosion around the patch. So really what they do is they turn the anodic steel into the cathode, and then the anode, of course, becomes the anode. So there's that electromotive series that I was talking about. So steel and zinc are different areas. The zinc is going to be more preferential in the presence of, if you have zinc and steel together, the zinc is always going to corrode first due to electromotive series. So now if we go back to that diagram that I had, now we have the repair area. It's chloride free, all the high pH, all of those things. But we put a galvanic anode in there. Now instead of the patch, the area immediately around the patch becoming the anode, the galvanic anode becomes the anode, and all the corrosion happens within that that confined system that we're putting there, and you protect the concrete around the patch area, and you prevent that, chasing the repair, where now you have a repair to do right next to the repair, and so on and so forth. You just have an anode. Now, of course, at some point, the anode is going to completely consume itself, and it's going to stop working. So it's not a forever solution, but, depending on the size of anode you use, it'll buy you an extra 10, 15, 20, 25 years of time before you have to worry about corrosion. So certainly going to buy you an extension of your service life over time. Here's a detail that I would, a typical detail that we have, just showing how you fasten the anode to the steel. There's different requirements as far as, having a standoff. You don't want the anode to be smashed right up against the steel. You want a little gap between that. That's to allow throwing capacity and different things I won't get into. But it's pretty simple. They're relatively cheap, easy way to do it. And you prevent that growing problem. We have our MAPEI Shield I anodes. Ours are more of a rectangular shape with a hydrophilic paste. Very, very thin, much thinner than anything else you'll see on the market. So you don't have to create a patch that's quite as deep with our anodes. So anyone that's familiar with some of the systems out there, some of them you have to soak with water overnight before you use them. We don't have to do that either. Does have a little bit of chloride in it. That's the activator, but we're talking super tiny, small amounts. It's like dropping a grain of salt into the ocean. Really, that's the kind of chloride that we're talking about. So it's not, certainly going to cause like long-term issues in your host concrete. It's, some of the competitors that don't use chlorides try to make it seem like it's a real big deal. It's really not. Pre-packing of the anodes are not required. So a lot of high resistivity mortars, you have to actually pack with a lower resistivity mortar. We don't require that with our anodes. So you can get up to about 100,000 ohms. And again, it's the thinnest profile on the market. So it's a really great product. Certainly, if you're not familiar with them, we'd love to talk to you about those more. We do have a bunch of different sizes, anywhere from 70 up to 450 grams. So again, depending on how long you want that repair to last, we've got different options for you. There's rebar coatings. These work similar to anodes. The idea really is the same. They're typically cement-based, often epoxy modified coatings that just encapsulating the rebar. They're also used sometimes as bonding agents. There's two different types, plural component and single component. More historically, the plural component were the ones that were being used. The issue with some of the plural component is you really got to time it well. They're used as a bonding agent, but there's like a window of time where it's a bonding agent. If you go too soon or too late, it's actually a bond breaker. So you really have to do a lot of planning. It can be kind of a nightmare. So we've come out with these single component products where you can really just go anytime, whether it's 2 weeks, 3 weeks, a month, a year. It will still act as a bonding agent over time. So it's a lot easier to work with. We've got our Planabond 3C, that's the 3-component one, and then the 1K is the single component. It's got a kind of blue hue to it. But again, while we're not putting an actual anode here, we're preventing the electrons from kind of flowing from the existing, from the new patch into the existing area. So you're creating that barrier. If it's just a small patch, like the one on the left there, you don't really want to go create more of a problem. So you don't have room for an anode there. You could use a rebar coating in lieu of an anode when you have real shallow patches or just real small areas. And then just lastly, real quick, we have our surface applied inhibitors as well. So these are, they're basically clear liquids that we tell you to throw on your concrete and it's going to solve all your problems, which sounds great, I know. But they do work, despite the kind of, I joke slightly about that, but basically what you're doing is you're putting a liquid onto the concrete. That liquid is thought to penetrate into the concrete and reach the reinforcement steel, where it then will basically prevent, it repassivates the steel, makes it, recreates that passivation layer. That's the idea of it. The products were actually created by 3M years ago, when the electronics boom started in probably mid to late 80s. We were buying all these electronics from Vietnam, Korea. Well, they bring all those electronics overseas in the ocean in the container ships, they would open them up when they got to the US and they would all just be covered in corrosion. Well, we got all those airborne chlorides, you got metal, you got moisture, we've got all the things we talked about that are required to create a corrosion cell. So they needed to come up with a way to prevent all these electronics from corroding while they were being transported. 3M came up with this system where you just spray this liquid on them and it prevents the metal from corroding. Well, we took that technology and we moved it into the world of concrete and created these surface applied admixtures where you basically, instead of just spraying it, you pour it on the concrete, it penetrates down and gets to the steel. The question becomes, does it actually reach the reinforcing steel? There's really no good way to easily test for that in the field. So there's a lot of hesitancy amongst people, and that's fair. I mean, I can't argue with them. So one of the things we're seeing in the industry is the creation of these dual component inhibitors, where in addition to the amine group, which was the amine was what was getting down to the reinforcing steel and recreating that passivation layer. They said, well, let's add a silane to this whole system so that now we're waterproofing in addition to getting down to the reinforcement steel. The idea there is you keep the water out and you get to the reinforcing steel and you got a much more robust repair that should last, you know, and prevent corrosion by getting down to the reinforcement steel, and 2, by keeping the water out. And then the third kind of bonus to that is that you can easily test how far it's made it by just doing this small core, and then you can spray some water on it and you'll see the depth of hydrophilic layer created by the silane, and you'll know how far it got down based on that depth. So this is kind of where the industry is going. The single component ones are still available. They are very effective if they get to the steel. It's just a question of, do they get to the steel? But because of that, most manufacturers, ourselves included, are moving to this kind of dual component inhibitor where you get the silane added to some type of amine silane based corrosion product. So with that, I went a couple minutes long, but that's okay. We are at 10 minutes till. I'm going to take some questions. What I need to do is just find my way to the question screen, Q&A. There it is. Okay. I'm going to answer it. See, we got so far 12. Any questions that I don't answer right now, I will certainly follow up with you after. So don't panic if I don't read your question. I'll reach out to you after. I'll send you an email and respond to your question. But for now, I will just try and get through as many of them as I can. We got about 14, it looks like. So let's see. I'll pick one. So good question. It says, what happens to the zinc that disappears when acting as an anode? So that's a very good question. So we talked about when iron starts corroding, it expands and creates this bigger volume, and that's what creates all the cracking and basically all the problems that corrosion leads to in concrete. So one of the questions that comes up pretty often with zinc anodes is, doesn't the same thing happen there? Aren't we going to have this expansion of the zinc, and it's just going to take the same tensile forces, and basically, are we going to have the same problem, 5, 10, 15 years later when this anode stops working? The answer is yes. The same thing does happen to zinc, though it's not quite as dramatic. It's probably maybe just like a doubling in size as opposed to getting 10 times the size. However, the anodes, so in the case of our specific anode, we have this, it's like a hydrophilic paste material around it, but it's designed in such a way that the paste can absorb that expansion without, the whole anode doesn't expand. It kind of just stays the same shape, but it internally absorbs that expansion. Because it's just a paste, the zinc can expand into it without creating tensile forces outside of the anode. So you don't get the same thing. A properly designed galvanic anode won't have that expansive force that you get out of corrosion of the reinforcing steel. So the zinc stays there. It doesn't like eat itself and consume itself and just vanish into thin air. It becomes a zinc carbonate, just the same as the iron becomes a iron carbonate. but because of the engineering of the anode, it doesn't expand like you would just with a rusting rebar, and you don't have that same problem long term. So great question. It certainly comes up a lot, but it's not much of a concern if the anode is designed to work properly. I'm going to take this question here about epoxy coated bars, because that's a near and dear to my heart. The question is, how effective are epoxy coated rebar? Does the coating chip off by bending the bars? What's the difference between green and purple? Thank you for asking the question. So epoxy coated bars, if it's completely perfect and the coating isn't compromised, they work great. You have a piece of rebar that has no way for chloride to get to the steel. If the chloride cannot get to the steel, again, we talked about breaking the chain, the chlorides can't get there, there can't be any corrosion. So in theory, epoxy coated bars are great. But what the person, Amir, asking the question here is getting at, how effective are they really? Well, that becomes the question. So when you have epoxy coated bars, they generally make the bars, the rebar plant makes the bars, they throw them into a big pile. Then they go to the process where they get epoxy coated, and then they get thrown back into another big pile. So when the crane operator is just picking up these bars and dropping them into this big pile, is any of the epoxy chipping off? Probably. I don't know, but I would say probably. It's then going to sit there, and you're going to get dirt and dust blowing on it from just from the wind. Is that going to penetrate into the epoxy? I don't know. I would assume probably. You're then going to throw it onto a truck where it's going to get driven to the job site. It's going to bounce around on that truck. It's probably going to get compromised on that truck. Then it's going to get taken off the truck and thrown into a pile on the ground again, where it's going to get broken again. Bending the bars, they're supposed to bend the bars before they apply the epoxy. If that doesn't get done, yes, that would absolutely cause some cracking of the epoxy, so that would be of concern. Point being is that I do not believe that an epoxy coated bar that gets to the job site is 100% coverage in any circumstance, unless you unless you painted the epoxy on at the job site by hand with a paintbrush and made sure that the whole thing was completely covered. I can't see where you would ever have an epoxy coated bar that is completely coated, which begs the question, okay, well, now we have these little pinholes everywhere. That's like the worst possible outcome we could have, because all the corrosion is going to happen at that one isolated location. Because of that, some engineers will they stay away from epoxy coated bars. They want nothing to do with them. I know Florida Department of Transportation historically has not been a fan of epoxy coated rebar, and they are certainly dealing with a lot of corrosion down in Florida. In principle, they work great, but in practice, they probably don't work quite as well as we make them out to be working. So that last part of the question, what's the difference between green and purple? I honestly, to be honest, I don't know. It's probably just the whatever color the manufacturer used. One manufacturer put a green dye and another put a purple dye. I don't know that there's any chemical difference or performance difference in the two of them. I think certainly in the picture that I took, it just was a random just random sampling of bars that they took. That's the color they chose. So that's that one. Let's see, we got another one here. What creates or governs the difference in potential difference between the anode and the cathode? So that's a good question. So we talked about, the difference in potential is what drives the force, what's driving the corrosion current. So what is creating that difference is what's creating that potential difference is a few different things. It could be a difference in pH. So in the case of where we talked about just doing a repair and you simply remove the concrete and replace it, in that particular case, you have a really high pH. Remember, we said the fresh concrete right out of the bag is going to be about a pH of 12, maybe even 12 and a half, 13 sometimes. But then the surrounding concrete all around that's been sitting there and been carbonating for all those years is probably down around 8 or 8.5. So in that particular case, that difference in potential is the difference in pH. You have a really high pH patch material that's just been placed right next to a really low pH existing concrete that's maybe been there for 20 years. So in that case, the difference in potential is created by the difference in pH. Then you may also have differences in the case of like the galvanic anodes. When we're using anodes, the potential difference is created by the difference in steel. So in that case, we talked about the electromotive force. So zinc being less noble is much higher prevalence of corroding than the iron that's in the steel. So the potential difference is created by that difference in electromotive force. So there's many different ways, different things that can cause it. It could be pH, it could be dissimilar metals, it could be chloride concentrations in one area versus another, but different things happen in different places. Why in the middle of the slab does the corrosion happen, at the location it does versus 5 feet down the bar? We don't have like a really good handle on exactly why that is, but it just tends to, all the chlorides kind of gather around themselves, and they start to, it creates, they navigate, they matriculate to that area to almost create that potential difference. But as to why it would form where it does versus another one, we don't really have a truly great understanding of that just yet. We just know that it does tend to happen that way. But generally pH, the amount of chlorides, dissimilar metals, those are some of the things that would drive that difference. Okay, so it's 2 o'clock. I'm going to stop there. I would like to thank everybody, the folks over at Structure, certainly for putting this on, and all of you for giving me an hour of your day. Anybody that did ask a question that did not get answered, I will get a list of those questions and I will follow up with you sometime in the next couple of days and try and answer your question as best I can. So thanks, everyone. I don't know if Suzanne, you want to add a few words, but I appreciate everyone's time. Thank you.
Yes, thank you, Brian and MAPEI, for putting together this presentation. As I have been putting in the Q&A, it is being recorded and will be available on the Structure Magazine website, which is structuremag.org, within a week on the webinars tab. On behalf of Structure Magazine, I would like to thank you all for your participation in today's event. This does conclude today's program. Thank you and have a great day.